seems to be cooperating. We're recording. Okay, so a couple of announcements. I had said I was going to get your quizzes back today. If I had not been exiled from KL for 4 hours yesterday because of apparently nothing, with your quizzes locked in my office and me not in my office, I would have gotten those done. I stayed up extraordinarily late for Dr. Kinney last night and tried to finish them and promptly fell asleep. So I literally just have to add up points and enter them into Isidore. So if somebody is really dying to have their quiz today, you can follow me back to my office and I will do some math real fast and give you your quiz. I will post the grades by the end of today. So you will see your grade. If you would like your hard copy of your quiz, then you can come by my office this afternoon, after class if you so desire. Otherwise, I will pass them back on Monday. So apologize for that. I'm going to blame the hazmat crew or whoever it is that was here. So today we're going to talk about linear regression, and it's kind of building upon solving linear systems of equations. So you have to use linear systems of equations to do regression. And as a reminder, we have homework due Wednesday on linear systems of equations. And then I posted the bonus homework number 2, which is to write MATLAB code to calculate your final grade in this class. What I do, or what I guess the ulterior motive of doing this homework is that if you ask me what your final grade is in this class, I will ask you if you've written your MATLAB code to calculate your final grade. Beware that if you ask me what your final grade is or what I think your grade is going to be, I'm just going to ask you if you've done your MATLAB code. That's my reasoning for that. On our schedule, we have quiz number 5 next Friday. I think it's very likely we will not be ready for quiz number 5 next Friday. I'd like to give you guys an opportunity to do some homework on this linear regression stuff, which is what I plan on putting on homework number 5. So it's very likely that, well, I will say with 100% certainty quiz number 5 will not be next Friday. When it will be, I'll figure that out. So we'll talk about it next week, probably Monday, kind of make a decision. All right? Any questions before we get started? Okay. So like I said, today we're going to talk about linear regression. So we're going to start with our question of the day. So our question of the day, we said, imagine that we're considering bungee jumping for actual fun. And being an engineer, before we go bungee jumping, we want to understand how much force due to the air resistance that our body's going to experience during a bungee jump. So we also want to know how the force is going to change at different velocities that I'm going to experience while I'm bungee jumping. So how could we figure this out? We could go to the wind tunnel and we could design an experiment where we're going to measure the force of the air resistance for different wind velocities while somebody's bungee jumping. So we've got some data here that was collected at the wind tunnel. We've got velocity data and we've got force data. And so now we got to figure out what do we want to do with this and what kind of information can we get from this data. So we've plotted this data. We've got our velocity data on the x-axis and we've got our force data on the y-axis. And so if we kind of want to understand the general relationship between these two variables, how does changing velocity change the force that we have? And we want just kind of a general representation of that. We do what's called curve fitting. So we fit a curve to our data, and that helps us kind of understand some information about force and how it's related to that velocity. So what kind of curve might I want to fit to this data? A linear curve, an exponential curve. We could fit any kind of curve to this data. We have to figure out kind of what's the best type of curve to fit to the data. What's going to be the shape or the form of a curve that best represents this data? It might turn out to be a linear curve. It might turn out to be something that's a little bit nonlinear. We just kind of have to figure that out. And the best way of doing that is not to just slap some curves on there and look at them, but to actually quantify that and figure out what's the best curve to fit to the data. So we have a couple different ways that we can fit curves to data. So if we have some raw data like this in that picture in the center, we can do two different things. We can either do curve fitting via what's called regression or curve fitting via what's called interpolation. So with regression, we fit kind of one curve that's a best representation of all of the data that we have. And you'll see that that curve doesn't actually go through any of the data points. It just kind of is a best fit, an overall representation of what the data, kind of the trend of the data looks like. It's generally increasing as we increase, or the y value is generally increasing as we increase the x value, and that's what the regression kind of tells us. The other type of curve fitting that we have is what's called interpolation. And you'll see that we, now this curve is actually going through all those different data points. So it's not just a representation of overall in general, what's the x related to the y, but it kind of goes through and passes through every one of those data points. And so you see, even with the same data on the two different plots, we get completely different curves out of these two methods that we have. So some kind of basic differences between the two types of curve fitting. They both have predefined forms. So it's like we've got this certain way that we can do regression and a certain way that we can do interpolation. Regression generally fits all the data at once. So you get this one general relationship between all your different data points. And interpolation often fits the data in different segments. So we have, you know, kind of one curve going through maybe one or 2 points, and then another curve going through another set of points. Sometimes you can fit data to all the points at once. It just kind of depends on what type of interpolation you're doing. Regression, like I said, doesn't go through the points, so it's kind of trying to minimize error between the data that we have and the curve that we're fitting to it, where interpolation actually passes through all the data points, so there's no error between the curve and the different data points that we have. We're talking about a linear system of equations. So we use linear systems of equations to solve both of these types of curve fitting problems. We learned, and we've talked about up until this point, determinate linear systems of equations, where we had the same number of equations as we had unknowns. That's what you're doing on your homework 9. That is a representation of an interpolation problem. So interpolation, we have the same number of equations as we have unknowns. In a regression problem, we have what's called an overdetermined problem, where we have many more equations than we have unknowns. So we have to figure out kind of how do we set that up, how does that look a little bit different from what we know about linear systems of equations, and how do we solve those types of problems. So statistics comes into play with curve fitting. And so one thing that you might start thinking to yourself is, why is statistics related to curve fitting? Why is it important that I know anything about statistics? And it's because it provides a measure of objectivity and kind of reproducibility to this curve fitting process. So rather than just slapping up a curve on some data and saying, that looks okay, we've got ways that we can quantify using statistics how well that curve fits the data. And that helps us do this in kind of a repeatable way, so we can do it every single time we have a set of data. So again, it kind of helps us answer these two questions. How well does the curve fit the data, and how can I systematically and kind of repeatably fit curves to data? So that's what statistics do. So we're going to talk a little bit about statistics. So if we've got our data from the wind tunnel, what kind of information can we get from this data set? If you guys were given these numbers, what kind of statistical related things do you already know about that you could calculate from this data?
The velocity is increasing by 10.
So the velocity is increasing. Yep. So increasing by 10 every time. What other kind of statistical numbers could we potentially calculate from this data?
The
Average, mean, same thing. The range. So we've got a couple different things that we can calculate, and then there's some more statistical information that we can use to kind of quantify this. So another question to think about is, why do we measure more than one data point? Why not just take data point number 5 and say that's representative of my relationship between force and velocity?
You want to create a graph
Well, we want to create a graph, but we could put 1 point on a graph, right?
Yeah, but you may like want to see the relation to the different velocity or force maybe.
Right, so when we looked at that data, we saw that there wasn't a direct relationship. There's not a directly linear relationship between velocity. So our velocity is always increasing, but our force isn't necessarily increasing at the same rate as the velocity is increasing. So if we measure more than one data point, we get a better representation of reality. And why does that happen? Why do we get kind of this not so neat relationship when we go and measure things out in the real world? Any guesses? What, huh? There's a lot of variables, right? So there's a lot of different things that are affecting our measurements. What else is affecting our measurements? If I go down and I measure force of something, if I measure the force of one object 10 times, even the same object, am I going to get the exact same force values out of my measurement system? Probably not, right? There's lots of error associated with all sorts of measurement techniques that we have, especially in the real world. Even if you go stand on your bathroom scale 10 times in a row, you might get a slightly different number because the bathroom scale is just not that accurate. So you're going to always have some error. You're always going to have fluctuating conditions that are going to affect your different variables that you have. So if you measure more than one data point, you can kind of help smooth out some of that error and kind of account for that and say, now that I've got 8 data points instead of 1 or 2, it's going to help me kind of account for some of that error, and hopefully I get just a representation of my whole population or my whole sample without having to worry so much about where is that error coming from and have I counted for it directly. So we talked a little bit about how can we potentially summarize the data set with a few numbers. We said maybe we could calculate an average or a range, something like that. There are several other things that we can use to kind of quantify and take some information and get some hard numbers to talk about this data set in a quantitative way. So when we're talking about statistics, we kind of have to learn a couple vocabulary terms that are helpful. So a sample, when we're talking about statistics, represents repeated measurements of the quantity of interest. So we have our 8 measurements from the wind tunnel, so our sample size in this case is 8 because we have 8 things. And a lot of times in statistics, you'll see that represented by some sort of variable where you have, y 1 through 8 in this case would represent all of our different force measurements from the wind tunnel. And in general, people will use little n as the representation of the number of points that we have in our data sample. So the first thing that you're probably most comfortable with is taking an average. So when we take an average, that represents kind of the central distribution of our sample. So we sum up all the numbers and we divide by the number of samples that we have, and that gives us an average. If we had no measurement error, then all of our data samples would be the same, and we would have 0, our average would be the same as all of our data points. So if I were to measure myself on a bathroom scale, and it was a super accurate bathroom scale, I had no error, it would give me my weight. It would give me my weight 1,000 times. If I took the average of all those numbers, it would be the same as any one of those numbers. But what is likely that we're not going to have a system where we have no error. So our average is kind of a representation of kind of the average of all of that data. All right, so the other thing that you may be kind of familiar with is what's called a standard deviation. We often calculate standard deviation to represent kind of the variance or the spread of the data in the sample. So we get an average, but we also kind of want to know how much error is in our sample, and our standard deviation is a measure of that. So it tells us kind of away from the average, how much is our data spread out. Variance is another measure of the spread of our data. It's just equal to the square of the standard deviation. So some people prefer to use standard deviation. Some people prefer to use variance. They're kind of the same thing. Variance is just a square of the standard deviation. We also have something that's called the coefficient of variation, and it's based on the standard deviation also, and it's just kind of a normalized value. So you calculate your standard deviation, you divide by the average, you multiply by 100, so you get a percentage of that spread. So these are just 3 different ways that people quantify kind of the error in your data, and it just kind of depends on who you're talking to, which is their favorite measurement for error. So we're talking about statistics, what does that really mean? So if we have what's called a normal distribution of our data, we have our average, that's what falls into the middle here. So if we look at our normal distribution has this kind of bell shape, our average value right here in the center of the bell shape, and they say that 68% of your data falls within 1 standard deviation, so 68% of your samples is within 1 standard deviation, and then 95% of your data is within 2 standard deviations. And that's kind of where the standard deviation comes from, is that it has this normal distribution, and that's kind of where your data falls into. So just kind of some information, statistical information that's good to have. So how does this relate to linear regression, and what is linear regression? So when we talk about linear regression, our goal is to find the best fit or linear fit to a sample of data. And like I said, we want to do this in an objective way so that every time we do it, we always get the same information back out. So we're going to use our statistics to be able to do this. So how do we accomplish this goal? So we need to pick the type of best fit curve to fit to our data. And then we need to evaluate how well that curve fits our data. So when we're talking about picking the type of best fit curve, we're talking about, do I fit a linear straight line? Do I fit an exponential? Do I fit a nonlinear curve that has maybe a second or a third power in it? Do I fit something that has some sort of like trig function, like a cosine or a sine in it? What's the type of curve that I want to fit to my data? The type of curve is typically like either given to you, or you want to solve a certain set of curves. So in this class, I'm going to tell you what type of curve to fit to the data, and then you might have to evaluate which one you think is the one that fits the data the best, given all these different options. So we're going to start off working with the simplest type of linear regression. So that's just a straight line curve. People will often call this simple linear regression because it's the simplest thing that you can do. You can fit a straight line to any data set that has at least 2 points. And so a lot of people will start with that because it's just the easiest thing. If you get a pretty good representation with a straight line, there's no point in going on and doing something more complicated. So we've got our wind tunnel data over there on the right. So we've got our velocity data on our x-axis, and we've got our force data on our y-axis. And so the general form for a straight line is kind of in regression. We tend to use this form. You might be familiar with, y is equal to mx plus b, right? That's the general form of a straight line. This is just kind of another representation of that, and it's consistent with the way that we do linear regression. So with linear regression, we often use these coefficients, A's, sometimes you'll see B's or other letters, whatever people pick, but this is kind of the general form, and we'll use that for all the different types of curves that we fit in this class. So when we have our linear regression, our general form is y is equal to a0 plus a1 times x. So what does our a0 represent with our straight line? The y-intercept of where that curve hits the y-axis, and then our a1 represents the slope. So we're all familiar with the straight line, pretty simple to do. So how are we going to fit our straight line to our data that we have? So what would be our x and our y that we want to plug into this equation for our bungee jumping problem? What's our x variable? The velocity, and our y is our force. So let's write a general form. Y is equal to a0 plus a1 times x. And so our x is our velocity, and our y is our force. Can you see the green marker okay? It kind of looks funky from up here, but yes, no? No? Okay, I'll switch. We'll get rid of the marker. I picked that up in my other class this morning accidentally and walked off of it, so it's clearly not a good one. Okay, so we have our general form of our linear regression, and then we know that our x is our velocity and our y is our force. So we talked about, oh, I went backwards. So what are A0 and A1? We already talked about that. So our A0 represents our y-intercept, and our A1 represents our slope. So we need to solve for these things. We don't know what those two values are, the A coefficients, until we figure out where this curve is going to go on this plot, right? So we got to figure out how we're going to solve for A0 and A1. And so we're going to solve for this using a linear system of equations, and that's going to help us solve for A0 and A1. So we want to fit one curve to our data. And so what we want to do is we want to fit, I'm going to go back. We want to fit one curve to our data, and so we're going to have one equation. We're going to have one general equation to represent our one curve. So that means we're only going to have two unknown values. We're going to have an A0 and we're going to have an A1. Those are going to be the things that we want to solve for. So our unknowns are going to be A0 and A1. And our known quantities are our x data and our y data, which in the case of this problem we said were our velocity and our force. So what we're going to do, how we're going to solve this linear system of equations, is that we're actually going to make one equation for every data point that we have. So we have 8 data points that we got from the wind tunnel, so we're going to make 8 equations. But in all 8 of those equations, they're only going to have the same form, and they're only going to have the 2 unknown values. So we're only going to have 2 unknowns, but we're going to have a system of 8 equations. And so we're going to be able to solve for those 2 unknowns using all 8 equations at the same time. So how are we going to do that? What does that look like? So we have one equation for each data point. So one equation per data point. And they're all going to have that same general form. So we're going to have a y is equal to A0 plus A1 times x. And the way we're going to differentiate between our different data points is we're going to use kind of a subscript for our x and our y values. So our first data point is we're going to call x1 and y1. Then we'll have x2, y2, all the way to x8, y8, because we have 8 data points. So we'll have y2 is equal to A0 plus A1 times x2, all the way down to y8 is equal to A0 plus A1 times x8. So we get one equation for each data point. The only thing that's different between the different equations is the different data that we have in it. So the different x value, the different y value.
The A doesn't change with every point?
The A's are going to be consistent because the A is going to represent our curve. And we only have to fit one curve to this data. Does that make sense?
Yeah.
So the A's are going to be consistent for all 8 equations. So even though we have 8 equations, we still only have 2 unknowns. So we're going to have 8 equations and 2 unknowns. So with my 8 equations and my 2 unknowns, what type of linear system of equations did I say I had? Is it determinate, overdetermined, or underdetermined? Overdetermined, and the way you kind of remember that is that I kind of have too much information to solve for my 2 unknowns. So it's overdetermined. I've got too many equations and less unknowns. But that's okay, we can do that it's fine. We're going to find the A0 and the A1 that are going to satisfy all of these equations at the same time. All right, so now if we have our linear system of equations, what are we going to have to do to solve this? MATLAB, right? That's always the answer in this class. What are we going to do? We're going to use MATLAB. I even got somebody saying that in circuits, I think. I had somebody asked, one of the circuits professors asked, what are we going to do to solve this? And a student that was in my class yelled out MATLAB, and everybody who was in my class laughed because they knew that that's always the answer. Apparently other professors don't think that's as funny as I do. So anyways, so we're going to use MATLAB, right? So how are we going to use MATLAB to solve this linear system of equations? What do we have to do before we can solve it in MATLAB? What did we learn about linear systems of equations? How can we write them? Huh? We need to put them in matrix form. So we need to take these linear equations and we need to transform them into matrix form. So what's our general form for a linear system of equations? What's that 3 letters that we put together? The AX times B. So our linear system of equations in general is our AX is equal to B form. So we have to get these equations into this form. So how do we do that? Huh? Well, you're going to reveal the magic behind the MATLAB curtain, right? So there's ways to do this in MATLAB. We're going to learn the boring, long way to do it, and then I will reveal the magic of MATLAB to get it to do it for you. So we're not going to use polyfit yet, but we will learn that later. We're going to do it the old-fashioned way, and then we'll learn the benefits of MATLAB functions. So if I want to write this in matrix form, what's my first step? When I write equations in matrix form, what should I do? The x vector, right? So what's in our x vector? So which represent what? What quantities? I know, but what do we call those? Our unknowns, right? So our x vector always has our unknowns in it. So we say, okay, we have A0 and A1, and I put that in a column vector like that, right? And it doesn't really matter, right, what order these are in. I could do A1 and then I could do A0. We just need to make sure once we've set it that we go with it for the rest of time, right? So now if I need to get my A matrix, what should I be looking at to get my A matrix? Do I want to look at my known terms or my unknown terms for my A matrix?
The known, which is the Y and X.
The known terms for the A matrix or the unknown terms for the A matrix? Unknown terms. Unknown terms go in my A matrix. So my A matrix has stuff about the unknown terms in it. What does it have in it? Does it have A1 times X and the A0? Or what part of those unknown terms do I pull out and put in my A matrix? What did you say, David?
The X part.
The X part. What do I do with this term? It doesn't have anything multiplied by A0. A 1 or a 0 are kind of our options here, right? So if I were to stick a 0 in here, this term would go to 0, right? So I don't want to do that. I want to put a 1 in here. So you can think about this equation really as having kind of like a 1 in here that you're multiplying this by. So we have to have something in our A matrix to hold that spot. We have to have something to put there because there's an actual coefficient there, otherwise that term goes away. So in our first column of our A matrix, what do I want to put here? A 1. And then over here in my second column, I want to put x1. So what does this first row represent? First equation that I have. So every row in my A matrix represents an equation. So what do I put on my second row of my A matrix? A 1 and an x2. And then I keep doing that for all of my 8 equations. So I get 1 and x3, 1 and x4, 1 and x5, 1 and x6, 1 and x7, and 1 and x8. So I have 8 rows for my 8 equations. And what do my columns represent here? The unknowns. So I have 2 columns for my 2 unknowns. So when we solved the determinate linear system of equations, we always had a square A matrix, right? We always had the same number of rows as we had columns in our A matrix. When we solve an overdetermined system of linear system of equations, like we have in regression, we're always going to have more rows because we have more equations than we do unknowns. So that's kind of to remind yourself, you know, what is this linear system of equations supposed to look like? If I'm solving a regression problem, I should always have more rows than I do columns in my A matrix. Any questions about that so far? All right, so what do we have left? We have our B vector, right? What goes into our B vector? What stuff do we have left? All the known terms, right? And so what's our known terms in this case are all the things on the left-hand side over here. So all we have left are our y values. So in our B vector, we're going to have a whole bunch of y values. y1, y2, y3, y4, y5, y6, y7, and y8. One row for every equation that I have, and then it always has one column. So whenever we have a linear regression problem, our x vector, our A matrix, and our B vector kind of always have this same general form. We're always going to have more rows than we have columns, and the number of rows is going to depend on the number of data points that we have. So if I give you 50 data points, your A matrix should have 50 rows in it. And if I give you more or a different type of equation, we just have to change what is put into each of these different parts of our linear system of equations. So if I have an equation that has 3 unknown values in it, I'm going to have 3 things in my X matrix, I'm going to have 3 columns in my A matrix, and my B vector would kind of stay the same. So you're going to have to kind of figure out what's going to change about each one of these parts whenever we change the type of linear curve that we're, or type of curve that we're fitting to our data. Let's see, we walked through this. So let's start and kind of write our MATLAB code to see if we can figure out how to solve this linear system of equations. So we've talked about all this, so I'm going to get out of PowerPoint and we're going to go over to MATLAB. So just like we solved our linear system of equations that we did in class last time, we can use a script or we can use a function, whatever your heart desires. I'm not even going to bother to ask because I know everybody's just going to say script, so we'll do a script. So what should we do at the top of our script? What's the first thing we always do at the top of a script? Housekeeping tasks. So we'll clear CLC to clear out our command window, and then close all, because we might end up doing some plotting with linear regression. So what are we going to need for our to solve our linear system of equations? What are we going to have to tell MATLAB? Yeah, so we're going to need to kind of fill in some of these blanks. So we wrote our generic X vector, A matrix, B vector, but we're going to have to fill in for the actual data that we have. So we collected that data in the wind tunnel, so now we're going to figure out how we put that in here. So first I'm going to create vectors that have our force and our velocity data in it. And And our velocity data was nice and evenly spaced out. We had values that started at 10 and went up to 80 by increments of 10. So if I wanted to create my velocity vector, to do that, what kind of command in MATLAB would I use? Linspace or colon operator, right? Either one would get the job done. So with Linspace, I started at 10, I went up to 80, and I had 8 data points. Now, what kind of vector does Linspace produce? Does it produce a row vector or a column vector?
Oh.
Row vector, right?
Yeah.
Let's look at our vector, or our matrices and vectors here. What kind of form do I want my x data and my y data in? And do I want them to be in rows or columns? Columns. So it's usually easier if I set up my kind of input data or my initial data that I have in columns, just so that it'll make my life easier down the road. So what do I need to do to transpose this into a column vector? My apostrophe. And now I'm going to input my force data. So my force data was not evenly spaced, so I'm just going to have to brute force type that out. So our first point was 25. Then we have 70, 380, 550, 610, 1220, 830, and 1450. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8 points. Is this going to be a row vector or column vector? Column? It's going to be a row, right? Because I put spaces in there. So I want to make it into a column vector, so I use my transpose again. Or you could have put semicolons in between every data point, however your heart desires. So now that I've got my data in here, what should I do? Do I need to do anything before I kind of get to this stuff? Probably not. We'll see. Do I need to put my x vector into my MATLAB code? I need to tell MATLAB what that is. Yes? No? No. So we know what this is. We're going to use this information, but MATLAB doesn't care. It could care less what this information is. So we don't need to tell MATLAB what the x vector is. The things we need to tell MATLAB are what's in our A matrix and what's in our B vector. So we're going to first create our A matrix. So with my A matrix, my second column is easy, right? That's all of what data? My force or my velocity data? The velocity data. So I should be able to just stick in my velocity vector in here for the second column. What about my first column? It's all ones. Do I need to painstakingly type out 8 ones?
No, ones.
We can use the ones function, right? So we're going to take advantage of our ones function. So there was a purpose for me teaching you that way back when. It wasn't just to create random matrices of ones. So what we're going to do is we're going to use our ones function and our velocity vector. We're going to smush them together and make one big matrix. So we open our square brackets, and then we type out our ones function. So what do I have to tell the ones function? How many rows and how many columns? So how many rows do I have? 8. And 1 column, right? So kind of like for loops. What if I were to all of a sudden throw at you, now I've collected 2 more data points in my wind tunnel, and I go up and I change my velocity and my force vectors. So should I go ahead and put an 8 in here, or should I use some other function to help me decide how many rows I want? We could do length, right? So we could use our length function here. So that's what I usually do, just to make sure that I don't have to count to 8. I can let MATLAB count to 8 for me. So I'm going to take the length of which variable? Does it matter if I take the length of velocity or force? Nope. My phone is ringing. So I put in my length and my velocity, and I need to tell it that I want 1 column of ones as well. So I get 8 rows, 1 column, because 8 is the length of the velocity vector. Then I want to move over to my second column, and I want to put in my velocity data. So what do I have to do to move over to my second column? A space or a comma, and then I can just type in my velocity vector there, close my square brackets, and MATLAB will squish those two vectors into one big matrix. Now this is where people will get into trouble. So if they forgot to transpose their velocity vector, their input vectors, and make them into column vectors, they're going to get kind of a nasty message from MATLAB. So I'll show you what that looks like in a minute when we're getting ready to run. So beware, this is where it helps to kind of set up your input data as column vectors, because then you don't have to worry about making sure they're the right size at this point. So now we're going to create our B vector. And what data is our B vector going to have in it? The force. So I can literally just say B is equal to force. And because I already set up force as a column vector when I input it at the beginning, I don't have to change anything about it. I just tell MATLAB B is equal to the force. So now what do I want to do? Yeah, I want to solve for my coefficients, right? So what are my two options when I solve for my unknowns? The inverse and what else? Backslash. So we've got our two different options. Which one does MATLAB like better? The backslash. So from now on, I'm going to allow you to only use the backslash. We're not going to do it two different ways. There's really no purpose in that. So whenever we're doing curve fitting, we can just solve with our backslash operator. So we're going to solve for unknown coefficients A0 and A1 using the backslash. And usually when I'm doing this, I like to call this like x coefs or x coefficients, just so that I differentiate that from any other x that I may have floating around in my other things. So I like to just kind of be specific that that's going to be my coefficients. So I type what here? B backslash A or A backslash B? A backslash B. And make sure you use your backslash and not the division symbol. So what's going to be in x coefs? What information are we going to get? We'll get what we specified here, right? Does MATLAB know what those numbers are? No, they're just two random numbers to MATLAB. So we have to either tell MATLAB what's in them if we need to use that information, or we just know it ourselves. So it's really kind of useful whenever we do regression that we not just get numbers and kind of trust that those values were good, but we kind of evaluate and look at how well we think the curve fit the data. And so we can do this a couple different ways. We can use statistics, or we can just plot the data. That's kind of the easiest way. It's just, the old, does it meet the eye check? So we're going to plot our data with our curve on top of it and kind of see what it looks like. So first, if we want to plot just our data, kind of a scatter plot of our data like I showed earlier, what do we want to plot on our x-axis and what do we want to plot on our y-axis? So create a plot of the data. What variable do I want to plot on my x-axis? Force or velocity? Velocity, and then I put my force on my x or y-axis, and then what I'm going to do is I'm just going to plot these as data points individually without a line connecting them. And so in order to do that, we just specify the marker. So we could do, an asterisk marker. And if I don't specify a line style, MATLAB won't connect those dots. It'll just put the asterisks there, one for each data point. I can. It's not 100% necessary, but it's good. Good practice. Keep me on my toes. Thank you. So now if I want to not just plot my data, but plot my curve, my regression curve on top of that data, I'm going to add a second thing to my plot. So what do I need to do to add a second curve to my plot? Hold on. and then I'm going to have another plot command. So we got to figure out what's going to go into this plot command. What do we actually want to plot? We want to have, at the end of the day, we're going to solve for A0 and A1, right? We're going to get that information out of our x vector. That's what we solved for. That's what's going to be in x coefs. So if I wanted to plot a curve on a bunch of data, where am I going to get the data for the curve? I'm going to use A0 and A1 somehow. But I need points to put on my x-axis and points to put on my y-axis. Where are they going to come from? Our velocity and maybe our force, but is it going to be the force the force data that we have, or is it going to be kind of a different force value? Different force value, John's shaking his head. So where's that different force value going to come from? Where did our A0 and A1 come from? I didn't just make it up. Right, so it's from our general form of our equation. We said at the end of the day we're going to have one equation to put our two unknowns in, and that's going to give us the regression curve that we want to plot. So we're going to have an equation that looks like y is equal to A0 plus A1 times x, and we're going to plug in our values that we solved for A0 and A1. So usually what I do after I've solved for my x coefs is I pull both those values out and I save them in variables that are called A0 and A1. So if I want to pull A0 out of my x coefs vector, what row and what column do I want to pull out of x coefs for A0? First row, first column. And then A1 is going to be x coefs, which row, which column? Second row, first column, right? So we have second row, first column. So we got a column vector. So now if I go down here to my plot, I want to create a curve that has the form y is equal to A0 plus A1 times x. That's my generic form. What's that going to look like from my problem? So maybe instead of using y, I'm just going to say my force from my fit, or from my regression fit, is going to be equal to what? I've got A0, pull that out of my x coefs, plus A1 times x. What do I fill in for x here? Which variable do I already have that I should fill in for x? Velocity, because my velocity is my x data, so I'm going to fill in my velocity. And now if I want to add this to my plot, I'm going to plot velocity on the x-axis and force on, or the force fit on my y-axis. And then, I don't know, we'll do a green solid line. And now if we save this and we go to run it, we did everything correctly. We should get a nice plot with our data from our wind tunnel experiment in the blue asterisk, and then our regression curve, the green line, straight line that fits the data, or is the best fit of the data with a linear kind of curve to that data. So how do we do? Okay? All right, so next time, so Monday, we will talk about kind of how do we quantify, how do we use statistics to quantify how well that curve fit the data, and then, figure out what we need to do to kind of fit other curves to our data. So, all right, everybody have a fantastic weekend. And like I said, if you want your quizzes, you can follow me.